All right, well, welcome back. So we're actually going to be jumping back in time a little bit and looking at a very classic result in number theory. That is the ability or so-called inability to represent a given number as a sum of two squares. So earlier we saw this actually really nice connection to writing a given number as a difference of two squares. This was all nicely connected back into the world of factorization. So think back to Fermat factorization algorithm that ultimately led us towards this more modern approach, that is this quadratic sieve. But now we're going to change up that sign in the middle and actually begin to see some really nice connections to what ends up happening when we look at a sum of two squares. Namely, we're going to be looking at a really nice extension to this world of primality into other worlds. That is, certain numbers are actually going to lose their prime status when you actually jump up a given level. So numbers like 13, which we know and love as being a prime number down in the level of the integers, are going to lack this prime structure when we go up to something that's going to be referred as the Gaussian integers. And along the way, we're actually going to see some really nice, somewhat surprising connections to the world of lattices. So at the end of the last section, we actually saw that this subset sum problem can actually be reformulated as a question of actually finding short vectors in a given lattice. So this kind of really crazy little grid, what ends up happening is that I'm going to go digging in there and try to find things that are going to have really short length. So this question of actually finding so-called short vectors is a fundamental question in many of these proposed lattice-based crypto systems. The idea is that this finding of a short vector is genuinely going to be viewed as a challenging question. So the ultimate quest in all of this is actually to lead towards this development of some type of quantum resistant crypto system. So we need to recreate this notion of what hard actually ends up being. So this world of lattices has a bunch of really nice funky things going on, and it actually conveniently and somewhat cutely connects back to this world of looking at a classic question in number theory. This simple ability or inability to actually represent a given number as a sum of two squares. It also gives us a chance to kind of bring in a little bit of linear algebra and some of these lattices and see some of these very deep connections. So along the way, there'll be a few of these somewhat technical results. So I'll kind of try to kind of generalize or kind of give you an overall flavor of what's going on. I won't dig into some of those explicitly, but I'll kind of give you enough example to see all of these connections being formed. All right, so to start things off, let's just go ahead and think a little bit about this overall quest of trying to represent some numbers as a sum of two squares. So to begin, let's kind of just form a nice little laundry list of some classic examples to begin to see which numbers is this possible for, as well as some numbers where this is actually going to break down. So the first number we may think about is, let's say, the number 0. It's classic, it's simple, it's easy to work with, and it does have the ability to be represented as a sum of two squares in a somewhat trivial way. 0 is simply just viewed as 0 plus 0, and we can square those little zeros to see that it is properly a sum of two squares. So hooray, it all works, and everything is dandy for the number 0. It's actually a pretty nice connection. This ability to pad some of these little zeros around is actually going to tell us that any just pure perfect square on its own can actually be represented as a sum of two squares. For example, if I was going to look at, let's say, the number 9, we know that 9 is a 3 squared, which can then obviously be represented as a sum of two squares if I just pad it with this little 0 afterwards. So what that tells me is that any perfect square on its own can actually be represented as a sum of two squares just by simply taking the perfect square and then padding a 0 afterwards. For example, I could have the number 1, which is 1 plus a 0, and I can square both of those things to see, hooray, 1 is going to work. Well, this ability to be represented as a sum of two squares is not just going to be enjoyed by perfect squares already. We actually can kind of broaden our net a little bit. For example, I could look at the number 2 and see that this thing is actually going to be represented as a sum of two squares in, again, kind of a somewhat silly way. It's just going to be viewed as 1 plus 1, which is then going to be viewed as a 1 squared plus 1 squared, so that thing does properly work. Notice we don't want to think about 2 as being a perfect square on its own. You could think about it as a square root of 2 squared, but that square root of 2 is leaving this world of integers, and a whole bunch of bad stuff begins to happen once I kind of go up to the full world of real numbers. We kind of lose this notion of what it means to be prime, and a whole bunch of other bad things are going to happen. The moment I start allowing fractions and square roots, then if I give you the number 5, you could maybe think, well, 5 is going to be viewed as, 5 halves times 2, so it's no longer going to be prime, and a whole bunch of bad things are going to happen. So in this world, we do want to properly just live with the world of integers. The bases are going to be integers. The actual outcomes are all going to be integers. We're just going to be living in that nice little world. At the end of this section, we're going to begin to kind of elevate things just a little bit. We're not going to go full-fledged into the world of real numbers, but we will move into the world of kind of extending things just a little bit. What's going to happen is that we're going to take these classic integers and we're going to move to something that's going to be referred to as the Gaussian integers. And in that world, some of our favorite primes are actually going to break down. Something like a 5 is going to be prime in the world of the integers, but it's going to lack its prime structure when I go up just a little bit. So there is going to be some of this movement upwards, but we don't want to jump too far right away. So right now, it's just living in the world of integers and everything is great. So what that means for us is that if I look at, let's say, a number 3, I don't have the ability to represent this thing as a sum of 2 squares. One of the ways you can think about that is just think about all of the possible ways to add up to 3. It's too many pluses. Let's make that an equal sign. There's only really 2 different ways to add up to a 3. We can have a 3 and a 0, or we can have a 1 and a 2. And I don't really care about the order of these things, so you could switch them around, but that doesn't, take away from the fact that in either of those representations, at least one of the numbers is not a perfect square. For example, in the 3 and the 0, the 3 is not a perfect square because it's not. It's the square root of 3 is not an integer. And in the same way, the 1 and the 2 is going to break down for the exact same reason, is that 2 is not a perfect square because the square root of 2 is not an integer. So in either of those representations, we don't have this collection of 2 squares emerging. So what that tells me is that 3 cannot be represented as a sum of 2 squares, which is actually our first example of something that breaks down. And later on, we want to begin to think about which numbers is this going to work for and which numbers is this not going to work for. What you can see is that it's actually going to break down for some primes. So the number 3 is prime, and it doesn't have the ability to be decomposed as a sum of 2 squares. Whereas the number 2, which is also prime, but it's the kind of weirdo even prime, does have the ability to be decomposed as a sum of 2 squares. Later on, we're going to kind of actually have an ability to somehow split the primes into 2 little bins, the ones that have this representation and then the ones that don't have this representation. And it's a pretty clean line, and it's very simple to classify ones that will work and ones that won't work. But before we get there, let's kind of go ahead and think about a few other examples. So let's move it up to another even number, the number 4, which is a perfect square on its own. So it has that somewhat silly representation. So that works out great. And then if I look at 5, well, 5 is actually going to be 1 more than one of these perfect squares. So we know that it's actually going to work in a somewhat obvious way as well. I can just view this as 1 plus 4, because it's 1 more than the number before it, and that number before it is actually viewed as a perfect square, so I can actually write the 5 as a sum of 2 squares. So the prime number 5 is going to work. We saw that the 3 did not work, but 5 does work. So in the next slide, I'm going to begin to ask you to kind of separate these primes into these 2 little bins. So I want to start to kind of seed that a little bit. So begin to think, why is 5 different than a 3, as well as some of the other primes that we're going to see along the way as well. So next up is the number 6. I want to think about ways to represent the 6 and if any of those are going to work. 6 and 0, we have 1 and 5, we have 2 and 4, or we have 3 and 3. So the 6 is not a perfect square, so that representation is not going to create a sum of 2 squares. The 5 is not a perfect square, so that one breaks down. The 2 is not a perfect square, so that one breaks down. And neither of those 3s are perfect squares, so that one's going to break down. So 6 does not have this ability to be represented as a sum of 2 squares. So we have our first composite number where things break down as well. And one of the kind of nice connections to this is that if you think about how 6 factors as a product. So 6 is 2 times 3. And we just saw that the 3 breaks down, so there probably should be something underlying this world that says if the factors within the number don't have this ability to be represented as a sum of 2 squares, maybe there's something to the overall composite number not having this ability as well. It's obviously not a hard and fast true rule that if you have a 3 in your factorization, then you will not have this ability, because the number 9 obviously only has 3's in its factorization, and it actually did work. The kicker here is that the number of 3's that emerge is going to indicate whether or not this works. The only reason the 9 actually had this property is because I had 2 3's. So the 3 was already squared. I didn't have to go out looking for how to construct the square. It was already handed to me. So 6 doesn't work because there's going to be this single 3 inside of it. 9 actually does work because I have 2 3's. So the evenness of that exponent is going to come into play a little bit later, because I want you just to begin thinking about all of these little connections that are going to be formed. So next up, we got another prime, which is the number 7. And if you run through all of the possible ways to add up to 7, you're very quickly going to see that they do not generate a sum of 2 squares. 0 and 7, that won't work because 7 is not a perfect square. 1 and 6, that won't work because 6 isn't a perfect square. 2 and 5, that won't work because 5 and 2 are not perfect squares. If I looked at, 3 and 4, that won't work because 3 is not a perfect square. So we get another example of a prime number that does not have this representation as a sum of 2 squares. So somehow the number 7 and the number 3 should be living in the same world. So hopefully you can start to think a little bit about what world do those numbers happen to live in. So next up, we got the number 8. 8 is a 4 and a 4, or a 2 squared and a 2 squared. So yep, that one does properly work. The number 10 will work because it's 1 more than a perfect square. So that one has the somewhat trivial representation of just take the previous answer and add 1 to it. And then we're left to add another prime, which is the number 11. And if you cycle through all of the possible ways to add up to an 11, you have a few more examples to run through, you're going to see that none of them are going to work. So 0 and 11, 1 and 10, 2 and 9, 3 and 8, what do we have? 4 and 7, and 5 and 6. All of those ways to add up to an 11, all of them are going to contain at least one non-perfect square. So 11 is another prime that fails this property of being represented as a sum of 2 squares. We also have the number 12 is not going to work. So here's another one of these little blips where the singleton 3 is going to be living inside of the number 12. And because 3 doesn't work, 12 won't work. And then if we go up to another number, we're going to have a 13, which is actually another prime. This prime actually does have the ability to be represented as a sum of 2 squares. It's going to be the number 3 squared, or a 9, plus a 2 squared, which is a 4. So 9 and 4 properly does add up to a 13, so that one does work. And if you wanted to, you could kind of go through and form this massive little laundry list of things. You begin to see that I have an equal sign that's off in that one, but you can see that we're going to have some gaps being formed. You know, the number 14 won't work. The 14 doesn't work because it's connected to the 7 not working. The 15 doesn't work because it's connected to the 3 not working. The 19 is another prime, and we're going to see that 19 does not have the ability to be represented as a sum of squares. And then you see that we have a pretty big gap. The 21, the 22, the 23, the 24, all of them fail. The 25 is a perfect square, so one more than that also is going to work. And you can begin to kind of start to see this classification take shape.